A quick word about this video, this is the second part of the series, so if you haven't watched the first part, then I strongly recommend you go ahead and watch that first and then come back here so you can understand what we're talking about a little bit better. What's up everybody, welcome to part 2 of our physics series How to Animate Realistic Movement, where we talk about the importance of understanding the reasons behind motion and how it helps us to animate realistic movement more efficiently and with confidence. Here's what we're going to talk about in this video. We're going to talk about dynamic balance. What is action-reaction and how to apply it in animation. How to animate recovering balance. We'll talk about friction, and at the end we'll talk about breaking the laws of physics for cartoony animation. In part 1 of this series we talked about balance and how to make sure that our characters feel balanced in their poses, but that type of balance is called static balance, while dynamic balance occurs when the character is in motion, and the pose that could feel unbalanced for a stationary character can very well be balanced for a moving character. So remember we talked about the line of gravity, which is an imaginary line that goes through the center of gravity of the character and through the base of support. In order to achieve the dynamic balance, you can go two ways. First is tilting the line of gravity, or if you don't like it, the second way you can leave it alone and just imagine the forces that are acting here. So there is a centrifugal force that is acting like this, and then when we lean the character into the turn, we are throwing him out of balance and the gravity starts to help us fight the centrifugal force. The tighter is the turn, or the faster we run, the more distance we need to shift our center of gravity so that the gravitational pull can balance out the centrifugal force. The same thing goes for the character riding some type of vehicle or moving apparatus, be that a snowboard, bicycle or car. We need to lean into the turn to showcase the dynamic balance. And what's interesting here is, for example, if you need to animate two characters in a car, especially if the car is going fast like a car chase, making turns and braking and accelerating. So the way the driver and the passenger will behave should be drastically different, because the passenger rarely knows how the driver is going to operate the vehicle, while driver knows exactly about his or her intentions and prepares themselves to maintain dynamic balance, leaning into the turns, using the arms on the wheel during braking, while the passenger just abides the laws of physics and struggles to maintain balance all the time. Okay, so we talked about how to maintain balance in stationary poses or while moving. But what do we do when we need to recover from the loss of balance? What mechanisms do we employ as humans and what do animals do? But before we dive deep into that, let's talk about another important law of physics, Newton's third law. For every action force, there is an equal reaction force in the opposite direction, so there is always a pair of forces. Why is it important to understand? Because you can't describe realistic movement without describing the application of a pair of forces. And we'll start with a very simple example. When I'm standing on the floor, as a result of gravity, I'm exerting a force which is my weight on the surface of the floor. The floor surface is exerting an equal force on me, and that allows me to remain in place. Otherwise, I would go through the floor and accelerate towards the center of the earth. But what if I leverage the power of my muscles and push towards the floor? First, nothing happens, but if I push considerably stronger, I will jump. The result of this jump is the force that was acting on my feet when I was pushing down. And what happened is that my force that I produced pushed the earth down, and earth pushed me up, resulting in my acceleration towards the air. But the moment my feet stopped contacting the floor, I'm not acting on the floor anymore, and thus the floor is not acting on me. So what happens now is that the gravity of the earth starts to stop me and pull me back, and this results in opposite acceleration or slowing down. And once my speed reaches zero, I start to accelerate back down, like a bouncing ball. Now it's important to understand that I'm also exerting forces onto Earth. When I was on the ground, I was pushing it down. When I was in the air, I was exerting gravitational pull on Earth. But the Earth is so much massive than me that its acceleration away from me or towards me are completely negligible. So we as animators can't really show action-reaction principle on Earth, even though everything that moves around us moves because of this principle. We utilize action-reaction when we walk, the wheels of the car use action-reaction to propel the car forward, we use action-reaction when we swim to push the water away from us, but we can showcase the forces by getting the character into the poses that support that. And also we can use timing and anticipation for that as well. So here I'm crouching more to make a bigger jump, because if I'm jumping from this crouched position, I have more time during which I can produce the pushing force. And because I have more time, my momentum will be bigger. So I will be able to travel higher and I will be able to travel faster. So if you have a character that needs to jump over a large gap, for example, and you don't allow enough anticipation and time before the jump itself, it will never look realistic. And also remember that forces are always directional. So instead of pushing against Earth to walk, I can push against Earth to stop walking. Another important point of showcasing the action-reaction principle is interaction between characters. And this is not an easy beginner stuff material. This is very hard to do because not only you need to animate two characters instead of one, but you also need to showcase the interaction itself, the deformations that happen along the way, and things like that. But if you think about action-reaction principle, it's going to be a tiny bit easier. Now imagine you have to animate a fighting scene, for example, and one character is literally punching another. So you ask your friend to do a video reference with you. And obviously during shooting of this video reference, you are not going to punch your friend with the same amount of force that the other characters are supposed to. Ow! So this renders your video reference slightly useless because the timing and the poses, everything inside that reference is based on the fact that you are pretending to punch and not punching. But if you understand the action-reaction principle, that's okay, because you can modify the poses, you can modify the timing and the spacing, and you can modify the action-reaction, showing how the fist was really stopped by the body of the character, or even thrown back if you want a greater impact. There should be a consistent relationship. You can showcase action without showcasing the reaction, if you want to be believable. Going back to balance and what we talked about at the beginning of this video. When we are thrown off balance by an external force or as a result of us incorrectly struggling with gravity, we try to recover it. The most common mechanism for recovery is utilizing our body parts with the help of the contraction of muscles to shift our center of gravity into a position where it will be balanced. And without even realizing it, we're using the action-reaction principle. So imagine the character is running and then sees a gap and tries to stop, but because of certain circumstances, being unable to stop in time, loses balance. Here's what happens. What I'm doing here is I'm throwing my upper body forward and rotating my arms towards the fall, which represents action. And this action is causing the reaction in the lower body to rotate in the other direction, which successfully moves my COG back, allowing the line of gravity to land into my base of support and regain balance. Same thing happens here. This is the action and this is the reaction. Now, we humans don't have tails, and because of that we are much less graceful and constantly falling type of creature. Animals that have tails, especially long tails, have a much better balance, especially those who are walking on 4 feet. Not only their base of support is much larger, but they can use this tail to maintain balance all the time. So if you look at cats, for example, they are much more graceful, and they can maintain balance in situations where humans will fall instantly. So if you are animating animals, you really need to study their anatomy and how they use it to maintain balance. Now, friction is also the result of Newton's third law in action. Any surface is exerting friction on an object that's moving across that surface. If the object is not moving and just standing, there is no friction, but as soon as an unbalanced force starts to act on the object, the friction force will appear that will act in the opposite direction. And depending on the magnitude of the external force and the type of the surface, its composition and how uneven it is, the force will either prevent the object from moving or will resist the movement. So this is a very heavy thing. It's practically impossible to move. But there is a button there, and once you press that button, it adds an air cushion between the two surfaces, and after that you can slide it around easily. We usually think about friction and understand friction in relation to characters' feet. We understand that the feet should have a firm contact with the ground, they shouldn't be sliding around unless we want them to. But our feet are not the only parts of the body that experience friction. It could be our back when we lean against the wall, it could be our hand when we put it on the table, it could be our fingers when we slide them across the window glass. Anytime there is any contact with any surface, we need to think, okay, there should be some friction going on here. Even if it's ice or smooth surface like glass, for example, how do I show this friction? How do I need to change my timing and spacing in order to showcase this force? And that's exactly how you do this. You change timing and spacing to show the audience what type of the material is the surface made from. You know, if you want to animate a character on ice, or walking on a sandy beach, or touching something, the spacing and timing before the contact and after the contact are going to be different. You can bend the laws of physics if you want to, but it only works when it's intentional. For example, for comedic effect in cartoony stylized animation, this is a great tool and it works. Not because the audience or animators don't know physics, on the contrary, we know physics very well, and that's what makes it funny when things behave in unexpected ways. And we not just select to not follow the laws of physics in cartoon animation. On the contrary, we abide the laws of physics in cartoon animation, but when we exaggerate, we find places where to break those laws, and we usually save the biggest deviations from the laws of physics for the moments that need them the most. This is called contrast. And by the way, there is a video on my channel where I dive deep into the subject of contrast. If you haven't seen it, link in the description below. So this is what happens when we're doing this creatively and on purpose. On the other side of the spectrum is when we're breaking the laws of physics and still want our animation to be believable. And that's kind of pointless and will never actually work unless you are showing your animation to a very young audience who don't have enough life experience to judge. Because we as humans have a very trained eye when it comes to realism, and we know how things behave in nature. And when some cunning director is trying to fool us, for example in action movies, it immediately shows up as being fake, and usually the reaction is negative. If and only if it's not done on purpose for comedic effect, for example, like in kung fu movies when the bad guys are flying around the screen. It's funny because it's not real, and when something behaves differently from what we're used to, it becomes funny to us. I don't know why, but it works. Remember, you don't need to study physics in order to animate efficiently. You just need to think about general laws of physics whenever you are dealing with video reference, whenever you are dealing with body mechanics. And don't just rotoscope reference when the motion doesn't make sense to you. Look into reference, analyze it, and make conscious choices. As always, thank you very much for watching. Give me a thumbs up down below if you like this video, and I will see you soon.